Hi guys, my name is Jan and I'm going to be teaching you deep learning. So let's get on with the linear algebra. For the next duration of time, we'll be covering what is a matrix, what is a vector. Uh, Second point is how do we add, multiply, inverse. Again, like I said, for those of you who might have already seen this, please bear with us. What is inner product, norm, distance, what are orthogonal, and the most important for TensorFlow or for. So this chunk of code is just for visualization, how Python visualization, etc. work. I would not recommend you go deep diving into this. This is just for making sure the graphs are clean, the colors are good. Unless you really want to be like a heavy duty traditional Python programmer, I don't get this. But we've sort of just plugged in there for the sake of completeness. So I'm just going to go ahead and run this code. So from here is where you'll have to focus. So this is very important to sort of as a refresher. And for those of you who probably recall your high school math days, because most of TensorFlow code or deep learning code is basically based on tensors. Tensor is nothing but a combination of vectors. And so it makes sense to refresh this a little thoroughly. Yeah. So matrix is a simple rectangular array of numbers, and a matrix is a rectangular array of numbers. A matrix with only one column is a column vector. Notice how these are in bold because a vector has not just the values but also some direction. These are just two-dimensional vectors. These are vectors. Sorry, these are vectors in 3D. So in terms of notation, we will use uppercase letters for matrices and lowercase bold letters for vectors. So // v u means vector of u. So sometimes vectors that are 2 cross 1. So that's 2 rows, 1 column. So vector -2, -1 is also denoted as -2, -1. This is a small caveat because some languages like R, RStudio, if you work with them, they take this denotation. So it's a little useful to remember how the notations change. So -2, -1 can also be thought of a point as a plane. What does that mean? So if you take the origin and that point and you draw one line, that gives you the direction and also the weight of that vector. You can ignore hide code in slideshow. Basically what that function here about us is it draws and just puts it in HTML. So let's just go ahead and draw a simple point. So these are 3 points. Obviously, this is first quadrant, second, third, and fourth. Visualization is very important. I work in consulting briefly, and a lot of the time in consulting, the first thing that we had to go to was spreadsheets. Ironically, a lot of deep learning people do not use spreadsheets, but I find it very useful whenever in doubt to just go back and go to the basics and sort of really write all the simple weights or simple questions. So here is a vector. So this is 2, -2, -2, -1, 3, -1. In terms of the functions that we've written, I'll just go through on a high level. So ax.arrow is from the point 0, 0 until -2, -1, draw a vector. That's it. The width of that line is 0.2. The length of that line is 0.2. And write the head. That's pretty much what this guy does. Similarly, plot the axis. So this is just an axis. Plot the axis line. This is what I mean by axis. Plot the axis line from 0 to 6. Similarly, display the vector head as 3, minus 1. So here we are displaying that 3, minus 1. That's just how to sort of draw a matrix, a vector in Python. In terms of vector addition or geometry, again, referencing the syntax above. So we have a vector u, a vector v. We recall u plus v, which is also can also be denoted as this. This is u plus v. So matrix multiplication is the most important operation for matrices. As we recall, it's a little different from conventional multiplication of numbers. So a vector equation x1 a1 plus x2 a2 so on and so forth is equal to b can be written as a vector x equals b vector, where a is a1 a1 so on, x is x1 x2 x3. Recall that our weights in a single perceptron had a similar sort of form. So matrix multiplication, the definition is again AB equals A into B, and then you pass each of A. And we define the inverse of a matrix quite simply as A inverse. Matrix that is not definable is called a singular matrix. So what is an inverse of a matrix? When you take A and multiply with A inverse, you must get an identity matrix. Identity matrix is nothing but having the diagonal row as ones and the rest of the elements as 0. So inner product or the dot product. Now we have two matrices, 3, 5, 1 and 2, 1, minus 1, 4. So the sum of the dot products is nothing but take the first 3 into 2, 5 into minus 1 plus 1 into 4, and that yields a scalar value of 5. This is the inner product of the two vectors. Inner product, and recall that for a matrix, m cross n, if I need to multiply it with a new matrix, n cross p, I need to have the number of columns, which is n, the same as the number of rows. Okay, that's one small note that we need to remember. General definition of inner product is again x equals to so on is sigma xi of y. Yeah. Vector norm. Again, norm is just the modulus. So if I have a vector 3, 4, the norm of that is 5. So how do we get that? Very simple. So square root of 3 square plus 4 square. That's 9 plus 16. That's equal to 5. Okay. So vector norm is nothing but the modulus of that. Many times the norm is also the length of the vector. Again, this is the basic Pythagoras theorem. Won't look cool. So in a 3-dimensional space again, so you have one more dimension. Again, so it's square root of v1 square plus v2 square plus v3 square. So unit vector is nothing but take a vector and divide it by its length, or it's called a normalized vector. So let's say I have a vector 3, 4. The normalized vector is nothing but 3 divided by 5 and 4 divided by 5. That's nothing but second this divided by that's interesting. Why did this? Yeah, there you go. Okay, so 0.6 and 0.8 are the unit vectors of 3, 4. Is always, we need to deal with that one in other. So yeah, that's a good question. So Padam's asking, do we need to deal with vectors mostly in DL, other non-vector scenarios? So vectors are the foundation or the building blocks of TensorFlow. So a lot of TensorFlow or the deep learning libraries use a lot of matrix multiplications. So it's good to have working knowledge about these. You do deal with non-vector values also. That is after the deep learning library is used. So for instance, for the purpose of TensorFlow, we do deal with only vector values. But if you're working with the image problem, like if you recall the cats and dogs problem I had said, you have to deal with a lot of non-vector values. Yeah, so again, distance is a very useful, important building block of vectors. Distance between two vectors, 2 points, u and v, is just u minus v, the modulus. So when you take, let's say, we have two vectors. So I want to know what the distance between two vectors, namely 3, 4, and another vector here, 7, 9. So the way to get that is I take square root of the difference of each. Yeah, so that's the distance between these 2 points, 3, 4 and 7, 9. So if you have n points, it's just the differences, take the squares, sum them, and take the square root. Another way to view this is, v minus u square is nothing but v square plus u square minus 2 times u dot v. That's the dot product. So that's what he's written here. U dot v is the inner product which we have seen. For inner product, we just have to take each of them and take the scalar multiplications. Now we move on to just orthogonal vectors. So ortho means perpendicular. Orthogonal vectors are perpendicular vectors. What that means is take two vectors like u and v. If the angle between them 90 degrees. They're called orthogonal vectors. This is fairly straightforward. So how do we know two vectors are orthogonal? Two vectors are orthogonal if the inner product of them is equal to 0. Let's look at that. So one constructs an isosceles triangle centered at the point. Because the sides are equal, the two inner triangles are right angles. So the two blue lines are perpendicular if and only if the distance from u and p is equal to distance from u minus v. Okay. We've already seen the distance of u comma v is v square plus u square minus 2vu. Similarly, the distance from u to minus v is v square plus u square plus 2vu. So the distance of uv is equal to distance of u minus v. Therefore, these two terms must be equal to 0. Just a small proof on the derivation. So what we need to remember is just simple. Two vectors are perpendicular, then this is the most important thing. Dot product of u and v is 0. That's all. So the angle between two vectors is also important. The angle between two vectors is called theta. So here this could be theta. Yeah, there you go. And what that means is, if I want to find out the angle between A and B, I have this formula. Not so useful to derive it, but important to recall. So cos C is the theta that I mentioned, is A square plus B square, sorry, C square minus A square plus B square divided by 2AB. That's all. Here you go. So the angle of between B and U, and this helps in many ways because this helps how we take projections of V on U. It helps knowing if the vectors are perpendicular, etc. This is also called famously cosine law. So here you go. V minus U whole square is V square plus U square minus 2VU, which we looked. And so cos theta is U dot V equals divided by UV. So this is a very important method for finding out the angle between two vectors. So cos theta is just the inner product of the two vectors. Maybe as a small exercise, can you find out the angle between these two vectors, guys? As a classroom exercise. Just feel free to use your pen and paper and calculator. So yeah, so to find the angle between two vectors, as we saw cosine law, we really need to only take the dot products of the unit vectors. Are they unit vectors? We need to take the dot products of the unit vectors. That's all. So are they unit vectors? We can check. How do we check? But my favorite method is to work everything in an Excel sheet. What I do is, I go down, I first plug in the values of the vectors. 0.2 and 0.98. So I write 0.2, 0.98. Can everybody see this?
Yeah.
That's my first vector. Second vector is 0.95 and 0.31. I'm just going to also write 0.95.
0.31.
Yeah, 0.31. To check if it's a unit vector, what is this simple check? The sum of the squares should equal 1. Okay, so it's 1. Similarly, I just do this same operation here. This is also 1. So they are indeed a unit vector. Everybody following till here? Any question, doubt? Reggie, were you able to follow?
Yeah, go ahead.
Yeah. So first I made a small sanity check if they are indeed unit vectors. How did I do that? I simply took the square. This is the same process, this same fundamental you have to do. Just keep in mind fundamentals of basics. Even if you have a big tensor, what is a large tensor? If you have like 30 dimensions, you sometimes make sure that they're unit vectors. So it's very important to stress on the basics. Now that I know they're unit vectors, I simply do the dot product. Now what is the dot product? Dot. For taking a dot product, I simply take in the first value, the first coordinate of the first guy, and the second coordinate of the second guy, plus second coordinate into 0.4938. Perfect. Is this clear how I got this? I took 0.2, I took 0.95, and multiplied them. Similarly, I took 0.98, I took 0.31, and multiplied them. Both of those two I added. Same concept for even if it's a 100-dimension plane, 100-dimension vector. So same fundamentals even if it is 1 million. Okay. Now that I have dot product, I just do cosine inverse of okay, I think cos. I forgot the cosine inverse function. Let's just do it in Google. Cosine inverse calculator. Okay. So now that I have the value, I just do it's r cross x. It's not even r cross. So r cos, I put this value 0.4938, and I just want to get the angle 60.4 degrees.
Okay.
Oh, so Excel is useful. So turns out, in fact, r cos, a cos of 0.4938, it gave in radians. You have to multiply just with 60 degrees. So the value is 60 degrees roughly. So, yeah, so the unit vector is just the basic formula, right? So, for calculate the angle between two vectors, what I need to do is I need to first make the unit vector. Let me just annotate that here. To calculate, let's say I have a large vector like this and a small vector like this. And this guy is u, and this guy is v. Okay? So the formula states that first thing is I need to make unit vectors for both of them. And then the cos theta is the dot product of them. Why did I make it unit? Is derived from this formula. It's actually just this formula. That's it.
So as a first step, it should always be any coordinates given. It should be converted to the unit vector, and then we'll have to do the dot product.
Correct. Correct. Yeah.
Okay, got it. Thanks.
Oh, yeah. So in fact, it's also called scaling. So I think, have you guys come across scaling in machine learning? Like scaling or normalizing? Okay, no problem. So then never mind. So you're basically, some vectors might be very long, some vectors might be very short. what you're trying to do is standardize each vector. Let's say this guy was really long. He was like 3,000, 50,000. But this guy was only 1, 2. So what you're actually doing is both the vectors, you're getting them down to workable formats. So let's look at that as well. We have one very large vector, seemingly 3,000, 50,000. I have a big vector. And I have a small vector, 0.4, let's say 0.2, and let's just make it 2, 3. Can you see these two vectors?
Yeah.
Perfect. Now, obviously one vector, like I showed you, it's really large, right? And B is small, but still there will be an angle between them. To find out the angle between them, what I do is, first step, I need to scale. I need to bring down 3,000, 5,000, 50,000 to workable numbers. How do I do that? I first find out the, okay, now I scale it down. Did you see this? So 3,000, 50,000 is actually 0.06 and 1. Okay, similarly, 2, 3 also has to be scaled down to its unit vector. That, and then 3 divided by this guy. So it's 0.55 and 0.83. Now these two are workable numbers. Similarly, tomorrow you might have again hundreds of dimensions in your vector or matrices. Some vectors might seem large, some vectors might seem slow, but then you need to go ahead and find out the angle between them. The first step always is standardizing. It's also called normalizing. It's also called scaling, or it's also called unit vector representation. Now I can work with this. So let me go ahead and calculate the dot product. 1 second. So I'm going to do this first coordinate of first guy, second coordinate of second, plus second coordinate of second into second coordinate of second. 0.8637. So what is the function for arc cost? Okay, so the angle between them is 32 degrees. Does it make sense? From a seemingly very large vector and one small vector, I still was able to find out the angles because I knew how to standardize or scale it. Also, it's always useful to compare apples with apples. Okay. Here I had something very large of magnitude. Here I had something very small. I brought them down to two similar scales. Good question. Anybody else with questions?
Chen, in the dot product, while you were multiplying the coordinates of first with the second and then summing it up, I saw you multiplying by 60 as well. So why did we do that?
Sure, good question. So in this one, so 1 radian is roughly 60 degrees. Actually, we should multiply with 57.3. So Excel sheet gave me in radians. Do you remember radians? 2 pi radians is 60 degrees.
Okay, so basically we are converting the radians into the angle. Okay, got it. Yeah.
Yeah, so actually 57.3. Yeah, that's all. I converted radians to degrees.
One more question, Jayant. I mean, every time when we find the angle, it is always the cosine that we find, or we can also do the same thing with sine and tan as well?
So every time we are using the cosine law. to find cos theta.
Okay.
Once we find cos theta, we have to find theta.
Okay.
For sine, there should be some similar formula, but that's, I think, a little more complicated.
Okay.
From cosine law, we find first step cos theta. Second step is find theta.
And this theta is in yesterday's session wherein you had explained in the diagram of the perceptrons where theta is nothing but when it comes out as an output from H. Is it that one?
That theta, a good question. That theta is different from this because that theta is actually like an activation function. It's just written as capital theta. That is a word book. Good. Anything else? Okay, moving on. So next is least squares. So least squares is important. We see it recurrently, or we see sum of square errors, etc. Most of the loss functions or error functions are dependent on this. Okay, perfect. Yeah. So in many cases, we have a linear system. A into vector x is equal to vector b. Okay. Sometimes that equation might not be true. There could be some gaps. So we look at the error in that approximation. Okay. The least squares is one of the classic, like I said, errors. Sum of square errors is just nothing but sum of square errors. Square errors is nothing but predicted minus actual square and the sum of this for each point. Okay. Does this make sense? So basically what we're saying is we have some predicted set of points and then we have the actual points. We take the difference, square them and add them. That's it. One of the most commonly used methods of statistics. We'll just review that really quick. Again, a classic, at least my classic. So let's say I'm trying to predict your heights. The height of Padam, Regi, Papri, Arli. Okay. Now my prediction of the heights is, I say 160 centimeters, 162 centimeters, 158 centimeters, and 155. Hey, by no means I'm like, I'm just guessing randomly. So these are the 4 heights I predicted. So this is called prediction, okay? Now the actual heights, your actual heights were 159, 158, 161, and 163, let's say. So what is SSE saying? SSE is saying for each of the points, first I take the difference. So what is the difference of this guy and this guy? Minus below. Okay. So the difference is 1, 4, minus 3, minus 8. Okay. Now SSE is saying simply, I just take this and square them because I don't need negative values. I just square them and sum them. So I was off by 90 centimeters squared. Is this concept clear, guys? Because most of your statistics just deals with this. Like if this is the basic that just drives everything from artificial intelligence, machine learning, statistics, anything. If you know SSE, you pretty much know all of machine learning. Excellent. So similarly, he's just mathematically written it in a nice format, saying sigma yi minus bi whole square. Okay, sum of square errors. Now, like I said, this is the key principle. So minimizing my prediction function is the same as minimizing the sum of square error. So coming back to this, similarly the height example, I had some function called f of x that was trying to predict your height. Here the function was called gen. I mean, I just used a guess and predicted. Now I want to get better and better at predicting your heights. So what I have to do, I actually only have to minimize my SSC, right? That's all I need to do. I need to make sure, actually, ideally, my 90 should drop down to 0. That's the perfect function. But in reality, you never get that. But even if 90 becomes 80, that's great. Okay. So getting a better f of x. So I'm going to write a statement. Getting a better fit or f of x or a function or is the same as minimizing SSC, sometimes also called loss function. That's it. This is the hallmark. This is the key principle. So loss function, tomorrow you will see your TensorFlow running and the output will be, there'll be like loss function. So all the time, the most complicated functions till the simplest functions are only doing one thing and only one thing. What is that? They're trying to minimize loss function. So just think of your height example. I'm trying to predict four heights. I just randomly start guessing. But as time progresses, through some black box, some technique in deep learning, some technique in machine learning, I need to predict better, get my loss lesser and lesser. Okay, next. So minimizing loss function is also called optimization problem. The classic optimization problems like there's simulation, there's Monte Carlo simulation, genetic algorithms, etc. Traffic routing problems and optimization problems. So how do we go about it mathematically? There are two ways. One is geometric arguments based on projecting B on space A. Second is taking the derivative of the RHS expression and setting it to 0. We'll look at that a little closely. So again, this is a graph. So he's just simply taking a projection of B on the plane of X. Okay. So now we sort of move on to a very important topic called Eigen value or Eigen Decomposition. I'll give you a little bit of backdrop of what eigenvalue is, and so just I'll explain the concept of eigenvalue in the next step. First, I want to give you a little bit of the backdrop of the power of eigenvalue. So there's a very powerful technique, by far one of the most fantastic techniques ever to be discovered, or whatever you may call it, in machine learning. So machine learning is machine learning because of PCA. So PCA or SVD and even text mining. Why are we getting very good spam filters? Why are we able to use Amazon Siri, Echo very well? Is because of a technique called support principal component analysis. So PCA is nothing but principal component analysis. Similarly, SVD is singular value decomposition. It's also called LSI. It's latent view semantic, I think, indexing. So whatever it is, the key part of all these, SVM is a little different from SVD. Okay.
No, I have no idea.
No problem. Yeah. So I'm telling you so I'm going to explain a concept that is very, very important in machine learning and in deep learning. Like, so that changed the complete game changer for machine learning. So remember how we used to deal with hundreds, if not millions of features in machine learning. Let's say you're trying to buy a house or predict housing rates in Bangalore, in Bombay, in Hyderabad, wherever you might be. You have so many features. You have house, zip code, pin code, number of bedrooms, area, maybe if square feet, tiles, bathroom fittings. So all these are trying to dictate the price of the house. How do we know which features are important? You can't really obviously always take all the 100 features and try to build models, right? So even a human brain, like if you and your spouse go for buying a house, you're only looking at 3 or 4 elements. Do you see what's happening? Even though there are hundreds or thousands, the brain is only able to take 2 or 3 features. What are those key features? How do we get to that few features? Is called principal component analysis, or SVD. And these 2, 3, all of them are based on one concept. That's called eigenvalue. So let's learn what is an eigenvalue. I'll tell you one small example that will clear, and you'll know eigenvalue, and hence you'll know PC and SVD. Okay, that's all there is. Can everybody see this matrix? I've written a small matrix here. So I have a small matrix, 2 by 2, neat, nice. It's 1.36 minus 2.35 minus 2.35 and 4.18. Okay. This matrix is called X. I have multiplied it with a number called A. Sorry, I have a matrix called A, and this is my X. Sorry. Okay. Can everybody see this? Because this is a very important concept. Okay.
Yes.
Perfect. Yeah. So I have multiplied the matrix A with matrix X, and this is the value. So how did I get minus 0.99? I took 1.36 into 1 plus minus 2.35 into 1. So I got minus 0.99. Similarly, I got this other 1.83. Okay. Now, I want you guys, just as a small exercise, can you multiply 1.36 and minus 2.35 with this particular number? Minus 0.49 and 0.87. Just do it as a small exercise right now. Feel free to use Excel. Okay, so let me just discuss this. So what I'm going to do is, I'm going to multiply. So in matrix multiplication, remember, I need to multiply the first element, that is 1.36, with the first element of this. So I get 1.36 star this plus, I take this element and I multiply this. So I got minus 2.7109, which is what I've written here. Okay, that's I'm just going to make a red bubble there. Similarly, how do I get the second matrix element? I take minus 2.35 into minus 0.49 plus 4.18 into 0.87. Okay. So a simple check is, if I have a 2 cross 2 matrix and I'm multiplying with the 2 rows and 1 column, I should always get a 2 cross 1 matrix. So the thumb rule is, if I'm multiplying A, B with C, D, I should always get A and D out. Okay. Just remember that meme. If I multiply A, B, A cross B, and C cross D, I should always have A cross D matrix. Okay, A cross B dimension matrix multiplied with C cross D. The answer dimensions are always A cross D. Is everybody clear till now? Okay. Now to divide these two, so in matrix division, if I have to divide something divided by 5.51 or something, I just have to divide each element by 5.51. So how do I do that? I'm just going to divide this divided by 5.51 and I'm going to take this element divided by 5.5. So if you just recall, this is the concept. If I have to divide 4, 6 by 2, I just need to divide 4 and 6 with 2. I get 2, 3. Any questions up to here? Everybody clear? Everybody clear, right?
Yes.
Because this is very important. After this will be the concept. So, this, anything familiar? This 0.49 and so this matrix and this matrix, are they the same or different?
You see.
Excellent, they're same. So, see, just see this. These numbers and these numbers are the same. So, for a given matrix X, I have some matrix A that if I multiply, I get a constant times that X. So, for a given matrix X, which is my X, this one, if I multiply with this particular guy, I get some constant times that same matrix. What is happening for a vector A, if I have one particular special matrix, it's actually getting stretched. Can you see that? It's roughly 5.5 times that same matrix, right? So this special matrix, this special 2 by 2 matrix in this case is called the Eigen Vector. And the direction where it is going is also given there. And this is the Eigen value. Makes sense? For any vector in any dimensional space, this is only 2 by 2, I have a special matrix that if I just come and hit that with that vector, it just gets stretched. Okay, let's look at that a little more graphically. I have one more. Can you see this? What did I do here? For each of those points, vector points, I just went ahead and started multiplying with their eigenvalues. So a rectangle became a which shape? What is that shape, guys? What is the blue shape? Huh? Does anybody recall geometry? Yeah.
It's like a pentagon, you're saying?
It became a rhombus. Excellent. It became a rhombus. So rectangle can become a rhombus. So on and so forth. A pentagon can become something else. So there is a transformational matrix that stretches, rotates, and skews. Okay. So that is called the Eigen matrix, and that value to which it becomes that stretchedness is called the Eigen value. Okay. So this is very important and in fact this is so important that even people in biology are using it. Because in genetic, like biology, you're mapping genomes and all, you deal with hundreds of dimensions. Hundreds of dimensions are there, right? So you need to either stretch or condense it. So conversely, what can happen? If I have a big pentagon or a rhombus, can I multiply in a way where it becomes, if I have a big rhombus, I can make it into a small rectangle, and that's called principal component analysis. Make sense? Or singular value decomposition. I have hundreds of features in housing market, etc. But by applying a special matrix called the Eigen matrix, I can bring down to knowing which are the key components. Is it the area? Am I living in Panchankari or Kormangla? Am I living in, I don't know, Vadala or wherever? So the area, square feet, all that becomes important. Okay. So that's called Eigen properties or Eigen values. So here's the math behind that. We just looked at it very simply. In fact, you guys have done it yourself. So I have AX equals lambda X. A is just stretching that vector. And conversely, A is also condensing that vector. Okay. So this simple concept is even used in text mining. So text mining, you know how people use it? So you have like a review on IMDb, 1,000 characters long. Oh, people have written Bahubali 2 was insane, awesome, etc. Just apply SVD. Simply, it will just fetch the key values. No is a hit or no is a flop. That's all. Narendra Modi, is he going to win 2000 next election? Just look at millions of Twitter feeds. Just apply SVD. You pluck out the key values. Is he a hit in BJP or no? That's all. Okay, perfect. Yeah. So that's a little bit about eigenvalues and eigen decomposition. In fact, further there is a little more mathematical rigorous formula. You should just be aware of it. I'll show it to you. So this is called the eigen decomposition. Decomposition is actually decomposing into the parts. So how do we get eigen value and vector? Well, luckily Python, R, everything has functions. So this is a simple function. Just put eigen of, like it's really literally like this. Eigen of matrix A, let's say matrix X, will give you the eigenvalues of it straight away. So the decomposition formula, I'll just show it to you how to get that. So here we go. So V, there was V, we went and stretched AB. Similarly, there is AB, we can condense it back to V. Here is the more rigorous definition. So a matrix A can be written as the product of a matrix P into a diagonal matrix D and the inverse of P. That is the mathematical rigorous formula on how you get the eigenvalue, the eigenvectors, and the transformation. That's all. But the underlying concept is you have a small matrix. I multiply it with some magical matrix, which is called the eigen matrix. All it does is it stretches that. Perfect. So, in terms of this formula, this particular formula, key elements are, so D, so any matrix A can be written as P, D, P inverse. I'll just write in inverse as Pi, okay? So in particular, D are the eigenvalues. P are the eigenvectors. What else did we look at? This is the mathematical denotation. What else did we look at? This is particularly useful when we have hundreds of features, hundreds of millions of records, millions of features. I'll just review once more what is eigen, so that you guys can remember it. This is like the engine in every car, like the basic, and that's why even machine learning became very powerful. Until recently, when SVD and all was not discovered, there were a lot of drawbacks because people didn't know how to handle, large features. You really don't know. So in text mining, for instance, if you have large Twitter tweets, people are saying, I hate BJP, let's say, hypothetically. Some people are saying, I love BJP. So what does the eigenvalue decomposition do here? Luckily for us, it takes all those sentences and it starts building small phrases. So hate BJP, okay, it starts remembering. Love BJP, it starts remembering, so on and so forth. This is similar to that housing example. When we had a house matrix with so many features, area, square feet, bathroom tiles, floor, etc. What did it do? It started remembering, or it started figuring out automatically which are the key features. The key features are definitely location, square foot, so on and so forth. Okay, so that's the beauty of Eigen. We look at that example once more again. What did I do? So I have a matrix minus 0.49, 0.87. I just went ahead and multiplied with one particular matrix, 1.36 minus 2.35, this guy. I got back a 2 by 1 matrix. Incidentally, it turns out this is exactly 5.5 times that same matrix X. That's all there is. That is eigenvalue. So A into X gives lambda times X. And conversely, if we can stretch a matrix, we can also condense the matrix. Okay. Any questions, guys, here so far? On what is eigenvalue? What is the meaning of decomposition? What is the eigenvector? This is a very short interview question. Huh? For any good company will ask you this. They won't ask you like what is eigen. They'll ask you what is SVD, PCA, LSI. Excellent. So Padam's question is, we are analyzing weights of each value, and then whatever features we are having lower values, we will remove those features or apply algorithms. Yeah, see, so that depends on the problem again. So sometimes let's say we remove the features based on the business use case. Okay. So let's go to the housing example. Now the housing example, I had hundreds of features. Okay. I have hundreds of features. And then I had a model. Now that model predicted housing prices in that area in Bangalore using all the hundreds of features. It got hypothetically one accuracy, one sum of squared errors. Let's say that square errors was 100. Now 100 features gave an SSE of 100. But I applied an Eigen transformation, or what they call support vector, PCA or whatever. Now I got 20 key features. And I saw that even with the 20 key features, I was getting similar SSE, 100. Then I'll retain those 20 features. And I'll discard the 80 features. Okay. However, if I found that only 10 features was able to also give me SSE of the same SSE as 100, then I'll discard 90 features. So it's very domain dependent. Does it make sense? In fact, the onus is up to us to know how many features you want to remove or not. The eigenvalues will give you, the eigenvalues and the decomposition will give you the reduction in the features. You need to see how many features to remove or not. So for instance, another example is in genetic algorithms, in genome sequencing and all, you deal with 500 features. Sometimes it can happen, 50 features can explain all the variants. Sometimes it can happen, 100 features will have to explain the variants. So it depends on the data set also. Typically, lesser the features, the better. Why? Explicability is better, computational cost is lesser. So we always try to go with basics and try to make simpler and simpler models. Okay, guys?
Yeah, so when you said that if there are 100 features and it's up to us which feature to select, right? So is it always using this eigenvector or the eigen concept, or we can also use the p-values which we got to know during the previous sessions of machine learning?
Yeah. Excellent. Yeah. So p-values will tell you the feature importance, like the statistical importance of the feature. So, okay,
Okay.
I'll tell you the difference. So, basically, let's go with the Bangalore prediction of houses problem. Now, uh, you gave me a particular data set saying, Jen, these are the, I have 100 features and I have 1 lakh records. In that, one of the feature is square foot. Like it's a 3 BHK, it's a square foot or 2000 square foot. So I built one model. It turned out that so many of the values in the square foot were missing in that column. So then what will happen? The p-value of that column square foot will be not that statistically significant. You understand that?
Yes, yeah.
Yeah. But in an Eigen decomposition, it can occur that square foot was one of the important components or not, right?
Mm-hmm.
Yeah. So
Okay.
Eigen is a little different in sort of from the p-value. P-value is mostly dependent on the number of records.
Okay.
Eigen is a lot on the features and the feature importance.
So in real world scenarios, right, the data sets that we get in order to identify which features are actually important and useful to enable the model to perform better, right? So is it always suggestible that we go with the eigenvector decomposition?
Yeah, so all the best modelers, like I do a lot of Kaggle competitions, etc. And you will see also the first step. I mean, after doing the pre-processing, filling for missing values, doing step AIC, they straight away do PCA. PCA means the eigenvalue decomposition
Oh,
because simply of one reason. So something that has 100 features, which is what Kaggle typically uses, they straight away get it down to 20 features. And always, even practically, when you want to suggest to a client, client will only prefer smaller models, like smaller features. Uh, and even when you're trying to parameter tune or play with overfitting or underfitting, it's always better to deal with smaller, sizable features. Yeah. So they straight away do PCA.
okay. Yeah, got it. Yeah.
Perfect. Okie dokie. That's all for me, guys. Thanks. Bye.
Acadgild. Average is dead.